Every Linux system slows down eventually, and your job is to figure out why. Welcome to part 21 of the Dargslan series, where we move from running commands to diagnosing systems. Performance work comes down to 4 resources: CPU, memory, disk, and network. One method ties them together, and for each, there's a right tool to reach for first. Here's the path we'll walk together. We'll start with those 4 resource axes: CPU, memory, disk, and network. Then layer on the USE method: utilization, saturation, and errors, which is the single best framework for diagnosing a slow system. From there, we go tool by tool: top, atop, and vmstat for CPU, free and proc for memory, iostat and iotop for disk, and finally ss, iftop, and sar for the network. By the end, you'll know exactly where to look first. So let's meet the 4 axes. Every performance problem you'll ever chase lives in one of these 4 buckets. CPU is about code spinning or queuing for the scheduler. Watch for a climbing load average. Memory is RAM pressure, swap thrashing, and in the worst case, the killer stepping in. Disk shows up as slow reads and writes, with resize weight creeping up and the device pinned near 100% busy. And network is bandwidth, latency, and dropped or retransmitted packets, high round-trip times, errors in netstat. Identify which axis is hurting, and you're already halfway to the fix. Once you know which resource to look at, you need a framework to interrogate it, and that's where the USE method comes in. Coined by Gregg, it's 3 simple questions you ask of every resource. Utilization: what percentage of capacity is actually being used? Saturation: is work piling up in a queue, waiting its turn? And errors: are things outright failing? Dropped packets, I/O errors, kills. Run those 3 checks against CPU, memory, disk, and network, and bottlenecks have nowhere to hide. Let's start applying that framework to the first resource: CPU. The classic tool is top. Htop is a friendlier color-coded version, and vmstat gives you rolling per-second snapshots. That's what you're seeing here. Watch the R column for the run queue. That's your saturation signal, processes waiting for a core. And keep an eye on way. High I/O weight means the CPU is actually idle, twiddling its thumbs while the disk catches up. Finally, uptime gives you load average over 1, 5, and 15 minutes. Perfect for spotting whether things are getting worse or recovering. Since load average came up, let's decode it properly. Those 3 numbers are the 1, 5, and 15-minute averages of processes either running or stuck waiting. And the trick is to read them in context of your CPU count. In this example, we go from 0.42 up to 2.31, which tells a story. Things were calm 15 minutes ago. Wait, actually the opposite. Read right to left for history, left to right for now. So, load was heavy and it's recovering. Run nproc to see your core count, and remember, sustained load above that number means a queue is forming. From CPU, we move to memory, and here's where most newcomers panic for no reason. Looking at free-h, you'll see 8.2 gigs used out of 15. Sounds tight, right? But the column that actually matters is available. 6.4 gigs ready for any app that asks. That buff cache chunk is just Linux being smart, using idle RAM to speed up disk reads, and it'll hand it back the instant something needs it. Swap with a few megabytes used is fine. What you're watching for is thrashing. And that's where vmstat1 comes in, showing swap in and swap out per second in the SI and SO columns. Now, when the system feels sluggish but the CPU is mostly idle, your next suspect is disk. Run iostat-xz1 and look at 3 columns in particular. Percentile near 100, like the 97.3 you see here, means the drive is saturated. Your weight climbing into the hundreds of milliseconds tells you writes are queuing up and getting slow. And a high RS with a tiny RKBS is the classic fingerprint of random I/O, lots of small scattered reads. Once you've confirmed the disk is the bottleneck, Sudo iotop-o tells you exactly which process is doing the damage. Network troubles follow the same pattern. Start broad, then narrow down. SS-S gives you a quick connection summary, and SS-TNP shows you which process owns each socket, usually the first thing to check when someone reports a slow service. For bandwidth questions, iftop is essentially top for the network. Live per connection throughput so you can spot the noisy talker. And when the issue is reachability rather than volume, Misdata combines ping and traceroute to show you exactly which hop along the path is hurting. So when that dreaded ticket lands, the server is slow, resist the urge to guess. Walk the 4 resources in order. Start with uptime and top to see if load exceeds your CPU count. Then free-h and vmstat to check memory pressure and swap activity. Next, iostat-xe1. If %util is pinned near 100, your disk is the bottleneck. And finally, SS and netstat-s for connection spikes or retransmits. 5 seconds per step, and you've ruled out an entire resource access each time. Think of this as your cheat sheet for the rest of the journey. When you need a live process view, reach for htop or top. For per-second snapshots of the whole system, vmstat1. Disk stats come from iostat-xe1. And if you need to know which process is hammering the disk, iotop-o names names. For the network, S-TNP lists connections, while iftop or nethogs show bandwidth per host. For historical trends, sar-a. And when you're ready to go deep into a hot function, perf-top is waiting. Now before you start reaching for those tools, 3 principles will save you from wasted effort. First, measure before and after. Capture baseline numbers because feels faster is not data. Second, change one thing at a time. If you tweak 3 knobs and performance improves, you've learned nothing about which one mattered. And third, identify the bottleneck first. Tuning CPU when the disk is pinned at 100% accomplishes precisely nothing. And while we're on principles, let's call out 3 traps that catch almost everyone. First, panicking over high-used memory. Linux deliberately fills RAM with disk cache because empty RAM is wasted RAM. Look at the available column instead. That's what your apps can actually claim. Second, copy-pasting scictl tweaks from some blog post. Defaults are tuned by people smarter than us, so only change a knob when you've measured a reason to. And third, trying to diagnose a sick system with no baseline. Run SAR in the background during good times, so when things go sideways, you have something honest to compare against. With those traps in mind, here's a pocket cheat sheet worth committing to muscle memory. Start with uptime for a quick load average pulse, then vmstat1 for a live CPU and memory snapshot, free H to read the all-important available column, and iostat-xe1 when you suspect the disks. Reach for SS-TNP to see who's talking over TCP, and sar-a when you need to look backward in time. 6 commands, 4 resources covered. That's most of your daily diagnostics right there. So let's pull the whole part together. 5 ideas to carry forward. There are only 4 resource axes: CPU, memory, disk, network, and every bottleneck lives on one of them. The USE method gives you 3 questions per resource that catch almost everything. Trust available memory over used. When the CPU looks idle but the box feels sluggish, pursutal and funiowait will point you at the disk. And above all, measure, change one thing, measure again. That loop is what separates engineering from guessing. That wraps Part 21. And it brings us right to the doorstep of Part 22, the final project. This is where everything converges. You'll stand up a real VPS, harden the SSH access, configure a firewall, set up backups, and put monitoring in place. Applying every skill from this series on a live machine. 21 down, 3 to go. Take a breath, then meet me on the next one. We've got a server to build.